Hi, welcome. Today's lesson is on solving equilibrium problems. You should have already watched the equilibrium video, and maybe you still have questions on how you actually solve problems involving equilibrium expressions. So this video is just an added video in case you need some help with solving problems. So what kind of steps do I need to take to solve problems involving equilibrium? Well, the first thing I need to do is write the equilibrium expression. And here I've given you the generic one with A's and B's and C's and D's, but you will have equilibrium expressions with molecules like water or nitrogen or hydrogen or oxygen or something. But generically speaking, the equation goes the reactants on the left. Here I have reactants A and reactant B. And they make products C and D, but it's in equilibrium, so the reverse reaction is also going on. Don't forget the small letters represent numbers, like maybe 1 water or 2 oxygen. So A, B, C, and D, small letters, represents the coefficients in the equation. So here's the generic form. I have K equilibrium equals the products, which are C and D, to the power of their coefficients. Here's a coefficient, over the reactants multiplied together to the power of their coefficients. And the little box that looks like this means concentration using molarity. And don't forget, as we said in the other video, we don't include solids because their concentration is really not a concentration. You might have a density or something, but it's constant, so that's not included. Nor do you have concentrations of pure liquids, so they're not included in these problems. So you can kind of cross them off when you're writing the equilibrium expression. So let's go to the next step. After I've written the equilibrium expression, I'm going to substitute values that are given, the known values, and then I'm going to solve for hopefully the remaining variable, which should be just one variable. So in a problem, anytime you have variables, 3 variables, 4 variables, 5 variables, you need to know all but one of them to solve it. And at the end, sometimes I forget, but always remember to check your work. Now, I forgot to say when we were on this slide that I have 2 reactants making 2 products, but that doesn't have to be the case. You could have 3 products, so you could have EE here, all right? Or you could have just 1 reactant, so maybe you don't have a B, all right? So it doesn't matter. This is just a generic. So basically it's saying the products on this side, the reactants on this side, and the equation goes products over reactants to the power of their coefficients. So let's solve some problems now. Here's an example. What is the K equilibrium? And this one actually has KSP. Sometimes they change the letters by the K to represent a special kind of equilibrium. So what is the K equilibrium, or KSP in this case, for zinc hydroxide dissolving in water if the zinc concentration is 2.24 times 10 to the negative 6 molar and the hydroxide concentration, remember that brackets means concentration, is 4.48 times 10 to the negative 6 molar. So first of all, I need to write the equilibrium expression, but I need a regular equation to start with. So zinc hydroxide dissolving in water. So I have zinc hydroxide. It's a solid. And when it dissolves in water, we get zinc ions and hydroxide ions. And if it's saturated, it is at equilibrium, and I have arrows going both ways, right? So here we have the regular equation. Now I have to write the equilibrium expression. So I take the products. What were the products? I had a product of zinc. It was aqueous, so it gets included. And what was the coefficient? Well, let's go back and look. Just 1. Remember, if there's nothing there, it's assumed to be 1. And here I have hydroxide, and its coefficient is 2. And so I have hydroxide ions, and it gets squared over the reactants. And this time I only have 1 reactant, But look, the reactants is solid, so I don't even include that in my equilibrium expression. So what do I do with the bottom part? Well, you could think of it as being over the number 1 or just erasing that altogether. And that equals the K equilibrium. So that's the generic equilibrium expression for this. So I have 1, 2, 3 variables. So if they give me 2, I'm going to be able to solve for the third one. So what variables did they give me? Well, they gave me the zinc concentration. Oh, and here it says if the zinc, it should have said the zinc ion concentration is 2.24 times 10 to the negative 6. So we're going to put that in. So this was 2.24 times 10 to the negative 6th. And the hydroxide concentration was 4.48 times 10 to the negative 6. And you might recognize that that's exactly twice this. So why is it twice that? Well, in this case, every time a zinc hydroxide dissolves, I get 1 zinc and 2 hydroxides. So that seems to make sense. And that equals K equilibrium. Now this time I'm solving for K equilibrium, but I don't have to. I could have solved for the zinc or the hydroxide. So now I just plug it into my calculator. I get 2.24 times 10 to the negative 6 times 4.48 times 10 to the negative 6. Ooh, be careful, that should be squared. Equals K equilibrium. So if you plug that into your calculator, you should get 4.496 times 10 to the negative 17th. And what kind of units do we have? Well, sometimes actually K equilibrium, they'll leave off the units because they're kind of complicated and different for each one. But let's go ahead. If this was molarity, and this is molarity, I had molarity times molarity squared, which is molarity cubed, equals the K equilibrium. Now let's go back and do sig figs. I have 3 significant figures here, 3 significant figures here, so I just want 3. So how do I round this? 4.50 times 10 to the negative 17th molarity cubed. There we have it. We solved the problem. All right, hopefully you followed that and you're taking notes so that you can refer back to it when you have to do your problems. Well, let's solve one more so that you have a double practice here. So here the question is, what is the ammonia concentration in the following equilibrium given? Here's the equation, which is the Haber process. Nitrogen plus hydrogen make ammonia gas. All of them are gases, so that's important to note. It's at equilibrium, which is the only time you can use equilibrium expressions. That gives me the nitrogen, the hydrogen, and the K equilibrium. So what doesn't it give me this time? It doesn't give me the ammonia, so I'm going to solve for ammonia. So first of all, let's write the equilibrium expression. So I have one product this time, and it's ammonia. And I have 2 reactants. I had nitrogen and hydrogen. And that's going to give me the K equilibrium. Now I have to be careful because I have to go to the power of the coefficients. So I'm going to go look back what was in front of ammonia, what was in front of nitrogen, what was in front of hydrogen. So I had 1 nitrogen, 3 hydrogens, and 2 ammonias. 1 nitrogen, so I could put a 1 here, or that's always implied. And I had 3 hydrogens and 2 ammonias. So 3 hydrogens and 2 ammonias. So hopefully I'm not making you dizzy scrolling back and forth. So there we have our equilibrium expression, and now we just have to plug in the numbers. I don't know what's on the top, so I can leave it as ammonia squared, or if you want to shorten it and just call it X, because that's often what we call unknowns in math and science. So if I have X squared, which is really ammonia squared, I'm going to put it over the nitrogen and the hydrogen cubed. So the nitrogen was, and I'm not going to scroll back for you, but it was 4.2 times 10 to the negative 3. So if you want to look back at that, you can. And the hydrogen was 7.1 times 10 to the negative 1st. And we're going to cube that number. And that equals 1.5 times 10 to the negative third. So now I am going to solve for x. So I'm going to cross multiply. So 1.5 times 10 to the negative 3 times 7.1 times 10 to the negative 1 cubed times 4.2 times 10 to the negative third, and I get x squared equals 2.2548 times 10 to the negative sixth. And then I'm going to solve for x. So what is x? X is the square root of this number, and I have 1.5 times 10 to the negative third molar, because that's what we're dealing with, molar concentrations. So there you have it, a second example. So I hope you followed along, took notes, and now you can solve them for yourself. Thanks for listening.